All right, today's lecture we are going to explore a mystery. And to understand what that mystery is, let's first show you some things you already know. You know that the derivative of x to the 5 with respect to x, what is that? Well, it's 5x to the 4. You know that. And when it comes to negative exponents, when it comes to negative exponents, you know that x to the negative 5, let's say, with respect to x. If I take the derivative with respect to x, what do I get? Well, I get x to the negative 6. You always subtract 1, and then in general, what do we have? We have the derivative of x to the n. We bring the n down, x to the n minus 1. We can prove that always works, okay? But there's a problem. And actually that makes finding antiderivatives fairly simple for powers also. And that's where the problem lies. Because let's take a look. Let's take a look at the derivative of x squared. Now think about what that is. Right? Now let's take the derivative of x, just x. So x to the 1. What is that going to be? Now, let's go a little bit further. Let's take the derivative of x to the 0. Now, I claim that when you raise something to the 0 power, you will remember, matter of fact, I'll go ahead and put it, that's the same thing as just saying take the derivative of 1, a constant, with respect to x. And what is the derivative of any constant? What's the rate of change of any constant function? It's 0. So my question is what do we take the derivative of to get 1 over x, x to the negative 1? You would think it's x to the 0, but when the 0 comes down, you get 0 times x to the negative 1, it becomes 0. So does 1 over x have an antiderivative? Is there something that we can take the derivative of and get 1 over x? That's a good question, and we're going to use the fundamental theorem of calculus to say yes, there is. It just might not be as nice as we want. So what I've got here is a picture of 1 over t. I'm using t now as my dummy variable, right? So this actually is one branch of a hyperbola, and we've got a vertical asymptote at 0, 1 over 0, right? And what I'm going to do is define the integral from 1 to x. So right now I'm going from 1 to 1, so the integral of 1 over t dt from 1 to 1 is 0. Now look what happens as I move x over. As I move x over, let's say x to 3.480. So if I integrate from 1 to 3.480 of 1 over t, the area under the curve, between the curve and the axis is 1.247 something. Okay? So I've got a function. Right? I got a nice function that gives me back. Now notice, if we start at 1 and integrate backwards, we get negative values. Right? It gives me the negative of whatever the directed area is. So we know that 1 over t is continuous for any value greater than 0, so we know that this area exists for any value greater than 0, so we have a nice function here. Now we're going to use this function. We're going to give it a name, as a matter of fact. We're going to call this function the natural logarithm of x. Now we will explore later in another lecture why we call it that, but we'll define the natural logarithm of x as being the integral from 1 to x of 1 over t dt. Now the fundamental theorem of calculus says that if f is continuous over an interval from a constant to a variable x, then this thing has a derivative, and its derivative is the integrand back. It ties integration and differentiation. So in other words, for us, the antiderivative, if I take the derivative of this thing, if I do the following, if I go, if I go, if I take the derivative of the natural log of x, I get what? I get 1x. And that is what we wanted. Now Now we'll talk about why we call that the natural log in the next lecture. Thanks.